unfortunate. All right, so here's all the equations. Again, they're in an announcement I sent out. The constants are here, so yes, I will kind of put them again, but they're already here. So if you're like, man, I've got so much I want to put on my note card, use this to recognize maybe what you don't need to put. Everything on the board right now will be, literally this will show up, it'll look exactly like this on your test. As you can see here, R net equals R1 plus R2 plus blah, blah, blah. R net equals 1 over R1. You have to know which one's which, series or parallel. That's not here. Capacitor, same thing. You need to know which one's series, which one's parallel. I have 1, 2, 3, 4 equations for a magnetic field. Again, it's not labeled what they're for. One's a wire, one's an arc, one's a loop, one's a solenoid. So we're going to add those to our note card today, mainly just so I can label this is a wire, this is a loop, this is blah, 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 blah. My note card may be, so I know I give you all note card front and back. I may end up using more than 2 slides, mainly because I have to write bigger than you all, so you can see it, it makes sense, and it's not crammed in there. So just know that I'm not expecting you all, the one note card should be enough space for you all. I may end up needing more space just because of the way I'm showing it to you all. I have the utmost confidence you'll be able to be more efficient with your space than I will be able to be. So there's a lot of writing I have to do out. I'm going to do all the right-hand rules and write those out, and that just takes a little bit of space because I have to write a bunch of words. So with that in mind, we're going to go and get started. Like the last note card, I'm going to break it into sections. First is DC circuits. Next is forces due to magnetic fields. After that is sources of magnetic fields. And after that is Faraday's law, which is all that induction stuff that we did last time. I sent you all already a completed one. I'm basically going to be putting a lot of that on here as well and just giving some context. Giving some, hey, this is really important, or maybe a bit more details on it. But it's going to look very similar to what I already posted. So DC circuits. What do you all need to know for this? In a nutshell, you need to know series and parallel. What stays constant in series, what stays constant in parallel, and how to take a big circuit with a bunch of things and get it down to one element. That is very, very important, y'all. If you can do those problems in the problem set, you'll be good to go. Always, that's the rule. If you can do the problem set problems without looking at the solution while you're doing it, that's a great sign. That's why I give those to you all. That's the whole purpose of them. So, series. What does series even look like? It's one after the other after the other. No junctions between them. There can be a little elbow here, that's fine, as long as the wire doesn't split. In series, the net, you know what, before I even give you the equation for the net resistance, in series, current is constant. That's what you all need to remember for that. In series, current is constant. And the net resistance will be R1 plus R2 plus blah, 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 however many are together. While I'm pointing out, and as always, I'll also post this entire, whatever I do today will get posted online. In series, current is constant for resistors. For capacitors, charge is constant. So we talked about capacitors. There will be a problem on them. Not much, but there will be one. And in capacitors, it's that opposite. C net is 1 over C1 plus 1 over C2 plus blah, blah, blah. However many you have. 1 over Cn. Resistors and capacitors do the opposite things. All right. Series, current is constant, or capacitors, charge is constant. Resistors, add them on up. Capacitors do the 1 over, we call this the reciprocal, 1 over plus C1 plus 1 over C2. In parallel, so parallel is where they share the same voltage on each side. They share the same wire. It doesn't matter if that wire splits. So for example, this and How do I want to draw it? Sure, this one and this one. Those are in parallel. They share the same wire. It doesn't matter that that wire splits. All that matters is there's a black line, the same black lines touching both sides. And because of that, voltage is constant. Very, very important. Voltage is constant, meaning these both have the same voltage, meaning if I condense them into one, it also has the same voltage. Voltage is the difference between the two sides. They share the same sides, same voltage, same potential difference across them. R net will be the reciprocal, whereas capacitors will just be the simple one. Again, they flip. So 1 over R1 plus 1 over R2 plus 1 over blah, blah, blah. However many you have. Capacitors, there's no separate rule. Voltage is still constant. So I don't need to write anything extra there. Capacitors, the net capacitance in parallel, you just add them. They follow opposite rules of each other. Replace those capacitors with some, or those resistors with some capacitors, it looks the same. They share the same wire on both sides. So the challenge to this section is your ability to identify series circuits versus parallel circuits, and your ability to identify that current is constant in series and voltage is constant in parallel. That's the challenge for you all. If you can do the ones in the problem set, you will be good to go. Yeah?
Voltage is constant in parallel resistors?
Yes. And capacitors. Yep. And the logic to that, I'll draw some quick kind of colors on here. They both share the same voltage on this side, and they both share the same voltage on this side, so the potential difference is the same. A junction does not change the voltage. A junction, when the wire splits, the voltage is the same. Voltage doesn't care about a splitting path. You can think of going on a hike. Just because the path splits doesn't mean that one drops 10 feet. All that means is that now, a junction does change something. Think of again, if you're walking on a path and there's 2 paths to go, you have to go down one of those paths. In that case, you are the current. You are the flowing thing. You are the moving thing. If 10 people encounter a path that splits, some will go some way, some will go the other. Voltage is height, though. Just because a path splits doesn't mean one drops 10 feet down. One's a cliff and one's no. So, that leads us to our next little thing that we need to remember, the junction rule. Very simple, but make certain you can do it. The junction rule says that if current does come in, say it comes in here and it goes out like this, the sum of the in currents equals the sum of the out currents. What goes in must come out. I don't know how many people are in this room. Let's just say there's 100. You all came through 2 doors. Say 40 people came through one door, 60 people came in through the other. It doesn't matter what doors you go through at the end of class, but 100 people should leave this room. 100 people came in, 100 people go out. So, make up some numbers here. If 10 go in, and this one is 3, this one is 7. I'm just making up numbers to prove a point. What goes in must come out. The arrows that point in, you add those up, equals the numbers that goes out. We did a few examples of that in the clicker questions. Make certain you can do that. That will show up. Current is what's flowing through it. If a river splits, some water goes some way, some water goes the other way. We did not lose water, though. Voltage is how I like the height. Voltage is like height, current is like the flow. These are important things for us to remember because it's this test, and the final is cumulative, so we don't want to forget those things as well. Last thing we definitely need to remember, V equals IR, voltage equals current times resistance, and power equals IV equals V squared over R. I always have to double check these. I derive them every time I have to do them. I equals V over R, good job me, equals I squared R. I'm just deriving all three versions, just come from plugging in V equals IR. P equals IV is the OG. On the formula sheet that I gave you all, it will just say P equals IV. The other two versions just come from using V equals IR. If I plug in V as IR, you get I squared R. If I plug in I as V over R, I get V squared over R. I just give you all of them because why not? Either do the algebra or have it written down. The choice is yours. My feelings aren't hurt either way. Okay. And that's what you need to know about DC circuits. All of them boiling down to series, parallel, and yes, that junction rule kind of chalked in there as well. Junction rule is pretty simple though. You all could probably do the junction rule if I just gave you that problem and didn't teach you anything. What goes in must come out. Matches everything you've used to in life. All right, now we get to the magnetic field stuff. And if we have time, this is what I'll probably just spend the last part of class doing. Literally just a bunch of right-hand rule problems because I think those are going to be the hardest for you all. And the beautiful thing is we can write the right-hand rules on our note card. And I will. You can do whatever the heck you want. So we will attempt to not freeze things. That would be, at every step, I'm just going to save this because you all can see my beautiful organization. We are going to save this because I cannot promise that my computer won't get very upset at me. There you go. You can see that there's a bunch of versions. Oh, you can't even. Oh, nice. Okay. I don't want to have to redo this all later. All right. So, next thing we're going to do is forces due to magnetic fields. So, forces due to B. Hopefully we know that B is magnetic field. If not, you should know that. Forces due to magnetic fields. So the first thing we learned when we did the forces due to magnetic fields was actually the equation for it. Why was the first thing we learned the equation? Because we need to recognize it was Q, V, B sine of theta, where theta is the angle between V and B. And we learned that if the angle is 90 degrees, that's the strongest force. If the angle is 0 degrees, nothing happens. All right. I'm attempting to zoom in on the corner, and it's being very upset with me about that. So we may just have to stay in this view. Angle between B and B, it's going to mean I'm going to have to write a little bigger. Again, my space is not efficient here. I expect you all to be able to fit far more than I am on here. Woo. So, this just gives you the force. It tells you nothing about the direction. Just like every vector problem we've ever done, the equation does not tell you the direction. But it does tell you that if the angle between them is 0 or 180, if they are parallel or anti-parallel, no force. It does tell you that. So, how do we find the force, the direction of the force? Right-hand rule number 1. And I'm going to attempt to draw a hand, and it's not going to be pretty. Right-hand rule number 1 says, there's a thumb, clearly. Wow. I saw some, I'm actually stealing, I like the way someone else did it, so I'm doing it the same way. You point your fingers in the direction of the moving charge, so we call that either V or current. Current is moving charge. In fact, I'm going to jot this down some, because I'm going to give you all the other, while we're at it, let's just put both equations in the same place. That was the force on a moving charge. This is the force on a current carrying wire, ILB sine of theta. It's the same thing. Very often, I have actually done F over L, force per unit length equals IB sine of theta. I literally just divided the L, it's the same equation. But many of our problems, I said, find the force per unit length. And it's F over L. I just divided the L over. Same equation, force per unit length. Force per length. So if the problem asks for force per length, ID sine theta. This doesn't find forces. Check out some of the previous problems for clarification there. But so anyway, back to right-hand rule. I just put the equation up there because you use the same rule for both things, current carrying wire or the other one. So your fingers point in the direction of current, your palm points in the direction of the magnetic field, and your thumb gives you the direction of force. There you go. On a positive charge. This is the force on a positive charge. If negative charge, force is in opposite direction. We've done problems with that, but please don't forget that. Right hand is positive. If you really want, you can use your left hand for negative, but you could just use right-hand rule and say it's the opposite way. So if I have a charge moving to the right, with a field moving into the page, my thumb points up, a negative charge would actually experience a force down. Opposites. And I will write it explicitly here. Again, write whatever the heck you want on your note card that works for you. I'm going to write more than less. So I'm going to end up using more space than you will actually need because I'm going to try to put as much as possible and you kind of decide, oh, I like this, I don't like this. Do what you want. Fingers in direction. I'm just writing in words what the hand is showing. Fingers in direction of V or I, depending on the problem. Palm in direction of B, that's the magnetic field. Thumb gives direction of force for positive charge. Thumb gives direction of force for a positive charge. Highlighting that because please do not mix those things up. It's a really easy mistake to make. You're doing the right hand rule correct. You get the direction of the thumb. You say the force is up, but it was a negative charge the whole time and the force was the other way. And then you're sad because you get the question wrong. Whether or not you know you get it wrong is a different story. But like the last test, I will post the solutions to this test once everyone's taken it, which will be, I have some makeup test next week, same as before, due to excused absences. Yeah, we'll call them absences. So I will post the solution. I won't be able to post the solution until the end of class next Thursday. So just keep that in mind. But I've already made them, so they're done. All right, ready for number one? Find the force and moving charge. Yes. You can also curl them towards B. In our case, Everett, that's a great question. So you have fingers in the direction, you swing them towards B, your thumb points in the direction of the force. In our problems, the magnetic field is always perpendicular. So you can just say your palm points in the direction, and that's a little simpler. Yeah. Yep, this is the one where point your fingers direction, swing your fingers towards B. That works. It just ended up being that, oh, B is always in the direction. Your fingers always swing towards the way your palm is pointed, so you could just use that as well. Yep, good point. All right. Random rule number one, done. Sources of magnetic fields. The only other thing one more thing we need to fit on here, which will not fit. I'm going to put on the next slide. I was so close. I almost fit everything. Forces due to B, continued. The only other thing that you need to know is if you have a charge moving into a magnetic field, Here's a positive charge moving into a field. Say that field is going into the page. What happens to that charge? It experiences a force, but it continues to experience a force. And what shape does it make? A circle. A charge entering a field will go in a circle. I have to do the right-hand rule to figure out the direction of the circle. That is an important skill that you need. So, this is good practice. Which way will that circle go? Fingers in the direction of the charge. Magnetic field is into the page, so my charge will experience a force up. So it's going to start to go upwards, and then you can kind of complete the circle that would form from that. I didn't give myself enough space. What a beautiful circle. A positive charge will end up making a circle in this magnetic field, and that equation was QVB. Literally, the force due to the magnetic field, the one I already gave you, equals mv squared over r. The radius of that circle. This equation does not tell you the direction of the circle. It just tells you there will be a circle, and you can calculate the radius and the mass or whatever, given all the other variables. To find the direction of the circle, you're going to have to do right-hand rule. Like last test, half the questions on this will be ones that you can do without a calculator. A lot of them are going to be right-hand rule related. Okay? Because that's probably the most ones we've done without a calculator. Look at our clicker. Those ones actually show up on the problem set, but look through the clicker sets and things like clicker problems and whatnot. So there's our circle. Only other thing we need to mention here. I think there was one more thing. Oh, yeah. This isn't even going to show up. So I'm not going to even put it on here. I'm going to put it on here. It's not going to show up on the test, but it's useful to know. This came up with the thing. Magnetic field lines point out of the north end of a magnet and into the south. There you go. It didn't take much extra space, so I'll just chuck it there. That did come up in your all's problem sets. I do not believe there's any question on the test that requires you to know that, though. It is a very simple rule. Out of the north and to the south. Be away. Yeah, the picture does a better job than any word I can use. Out of the north and to the south. All right. Cool. Force is due to be done. Halfway there. This test, in my opinion, mathematically is easier than the first test, but conceptually is more challenging. So maybe that'll be better for you all. Maybe I have no idea how it's going to. We'll find out. I hope it's better. I want you all to do well. So if math was your challenge in the first one, hopefully this will be a little easier. All right, next is sources of magnetic fields. Sources of magnetic fields. Magnetic fields make charges move. How do you make a magnetic field? One way is a permanent magnet, but that's lame. You can't really make a strong, you can make a decent field with a permanent magnet, but really not that strong. You want to make a strong field, you need to run some current through a wire. Current through a wire makes a magnetic field. So we have our four situations. We have a straight wire, some point P, some distance R. Magnetic field is mu naught I over 2 pi R. You can use a capital R, a lowercase r, who cares? R, it's the distance from the wire to that point. I'm going to go ahead and give you all the equations. These just tell you how strong it is. They do not tell you the direction. We'll do right-hand rule 2 next. We'll draw that off to the side. But cosine or tangent,